Hi everyone, for this video we are going to cover section 5.1, Eigenvalues and Eigenvectors. And if you viewed the required viewing prior to this video, the clip from Avengers Endgame, at about the 23-second mark, Tony Stark asked his computer, it's not Jarvis, I can't remember the name, to give him the eigenvalue of that Mobius strip. And even though time travel doesn't actually exist in that movie universe, an eigenvalue is a key component to Tony Stark understanding time travel, and that's what you get to learn in this lesson today. So that's how super excited I am that I get to teach you about time travel in the Marvel Cinematic Universe. Okay, so we'll come back to what an eigenvalue is in a little bit. Let's kind of introduce it through an example. And I'm going to give you a matrix A that is 3, -2, 1, 0, and two vectors, U, that is -1, 1, and V, that is 2, 1. And in going through, and what we're going to do is compute A times U and A times V, and then kind of take a look at what multiplication by matrix A does to both of those vectors. And so if I take A times U, so I'm multiplying row by column, 3 times -1 is -3, and then -2 is -5, and then row 2 by that column, that row by that column, 1 times -1 is -1, 0 times 1 adds nothing to it. All right, so there's that one. And then A times V, 3 times 2 is 6, -2 is 4, 1 times 2 is 2, plus nothing is 2. There we go. All right, so that is our product there. And if that's what I was teaching you, that wouldn't be that interesting. But what I want to do is look at the original U. Whoops, I want my highlighter. I want to look at the original U and my modified U, my A times U, and compare that to my original V and my A times V vector, and kind of take a look, and while I'm kind of stammering on here, see if you notice what multiplication by A did to both of those vectors. And maybe by now you've kind of seen the connection here because you're all really smart humans. And if you take a look there at this product, what you see is that A times V, that is equal to twice the V vector. So it's scaled V by a scalar of 2, but it points in the same direction. And from U to A times U, the same thing did not happen. So here we will define our eigenvector specifically, what that means. An eigenvector of a matrix, of an n by n, so it has to be a square matrix, is a non-zero vector x such that A times x equals lambda x for some scalar lambda. So we use lambdas in as our notation for eigenvalues, eigenvalue, and that's what the next sentence says. That lambda is called an eigenvalue. So, and then the vector x was the eigenvector. And if there is a non-trivial solution of x such that A times x equals lambda x, because trivial, that's easy to find, that's the zero vector, but we want a non-trivial solution to that equation. Okay, such an x is called an eigenvector. So in the previous example, where we took A times V, and that was equal to twice V, in that example, the V vector is our eigenvector, and the 2 scalar is our eigenvalue. Okay, so what an eigenvalue does is it basically, when I multiply my matrix times the eigenvector, it scales. It kind of maps back onto itself, if you think about that whole linear transformation topic that we kind of encounter every so often. The vector V maps back onto itself, but scaled in some way. And to tie back into Tony Stark and time travel, if you've seen Avengers Endgame, you notice the problem that they have with time travel. When they sent Ant-Man, when they tried to send him through time in kind of the early part of the movie, he came back as like a little kid and then an old guy. They had trouble bringing him back to where he wanted, right? And so the idea that the matrix, the vector maps back onto itself, that's how they're actually connected. That silly thing in a movie is actually connected to the real word eigenvalue. And I think that that's super cool that some smart person that was making that movie wanted to have at least some semblance of realism, even though time travel obviously isn't real. That's pretty awesome. And then the word eigen, just in case you were wondering, is a German word, and it means own or like same. So the whole idea of mapping back onto itself is within that word as well. All right, in example 2, we are given a matrix A, and we are given into vectors, and we have to find out if they're eigenvectors of A. So determine if something is an eigenvector is relatively straightforward in that we take A and multiply it by U. Oops. And that's a 2. There we go. Negative 6, negative 5. There we go. We take A, multiply it by U, and then we take A, multiply it by V. 1, 6, 5, 2, and 3, negative 2. We find those two products, what that vector is, and check and see if it's a scaled version of what it once was. So A times U, row by column again, we have 6 minus 30 is negative 24, and we have 30 minus 10 is positive 20. And then 3 minus 12 is negative 6. 15 minus 4 is positive 11. Oh, that 6 should be a negative 9, rather. And so that is not equal to, that second vector is not equal to lambda times 3, negative 2. You can't multiply 3, negative 2 and get negative 9, 11, not by the same number. But the one above, A times U, that is equal to negative 4 times my U vector. So U is an eigenvector, yes. V is not. All right, now with this next example, we have the same matrix A, and we have to we have to show that 7 is an eigenvalue and find its corresponding eigenvectors. Okay, so this is a little bit more work to show something is an eigenvalue, and the where it comes from is this concept. 7 is an eigenvalue of A if and only if A times x equals lambda x, or 7x, has a non-trivial solution. So that is what we have to figure out in this problem. Does ax equal 7x have a non-trivial solution? So what we do is we solve. If ax equals 7x, I want to solve for x. So I'm going to subtract that 7x on both sides. Ax minus 7x equals 0. And then factor my x out on the right. A minus 7 times x equals 0. And it's not really just A minus 7. It's A minus 7 times the identity, because I can't just subtract 7 from a matrix. I subtract matrices from each other. So it's A minus 7i times x equals 0. So first, our next step is to find what is A minus 7i, and I'll write it out for this example. That's 1652 minus 7 times the identity puts a 7 on the diagonal and zeros everywhere else. So that, when you do the subtraction, is negative 6, positive 6, and 5, negative 5, which looks kind of cool. All right. And that is what we have to solve and see if we get a non-trivial solution. So I'm going to set up my augmented matrix, negative 6, 0, and 5, negative 5, 0. All right, my first row operation, well, I can just go right into reduced echelon form here. You can use the top row to eliminate everything in the bottom row when you divide out that scalar. So you get 1 minus 1, 0, and then 0, 0, 0 as your reduced echelon form. So do we have a non-trivial solution? The answer is yes. So at this point, I know that my vectors are linearly dependent. D-E-P-E-N-D-E-N-T. There we go. They're linearly dependent. So a non-trivial solution exists. Therefore 7 is an eigenvalue. Cool, we got an eigenvalue. Done. No, not done. We also have to find a corresponding eigenvector. The way that you do that is we take and represent the solution there we go, x1 minus x2 equals 0. So we clearly can see that x2 is a free variable and x1 equals x2. So the solution set to this system is x2 times the vector 1, 1. We've done that a few times. Okay. So then we can say, let's see, each vector of this form with x2 not equal to 0, because that wouldn't be a very interesting vector, is an eigenvector. Okay, so take any scalar x2, multiply it by my vector 1, 1, and what that produces is a vector who, when you multiply a by that vector, you just scale that vector. So you could take a times the vector 3, 3, or a times the vector 5, 5. Right? It's got to be some scalar times 1, 1. And all of those will map back onto themselves, just scaled by a factor of 7. Then we get to a little definition here. One more eigenword. Here we have the eigenspace of A consists of the 0 vector and all of the eigenvectors corresponding to lambda. So in the previous example where we had that it was x2 times the vector 1, 1, right? That any point on that line, any scalar multiple of the vector 1, 1 is an eigenvector for matrix A. Right? And so that line in R2 is the eigenspace of A. In this next example, we bump the degree of difficulty up to a 3 by 3 matrix. We're given that an eigenvalue of that matrix is 2, and then we want a basis for the corresponding eigenspace. So the steps are first to take A minus 2i, and that is equal to, if you do the subtraction there, you get 2, 2, 2 in the first column. You get minus 1, minus 1, minus 1 in the second column, and 6, 6, 6 in the third column. You can check my math there, but I'm pretty confident that I did it all right. And so then that matrix, that A minus 2i, because we have 3 identical rows, that reduces to 2 minus 1, 6, with a whole bunch of zeros below them. There we go. So that's what it reduces to. So then we take and we represent the solution to that matrix augmented with a column of zeros, and I'm going to skip right to the solution. You can go through the steps if you're not comfortable going right to this, but we have x1, x2, x3 is equal to x2 times a half 1, 0, plus x3 times negative 3, 0, and 1. And so again, if you're not sure what I did jumping from here to here, right, we augment with a column of zeros and solve for x1 in terms of x2 and x3 and represent them as that solution as vectors. All right, so let me drag this up a little bit. So our conclusion here is the eigenspace is a two-dimensional subspace of R3, and the basis looks like this, right? So bracket there, 1, 2, 0, comma, negative 3, 0, 1. And that is our basis. So it's a two-dimensional subspace of R3, and what that means visually is that any point on that plane, on the plane formed by those two vectors, any point on that plane is an eigenvalue of this matrix A. Multiply A by that vector, and you map it back onto itself, just scaled by, in this case, a factor of 2. Okay, so now we get to our first theorem in this chapter, which we will go through a proof of because it's kind of interesting, and it refers to finding eigenvalues. So far, we've done things with eigenvalues and with eigenvectors, but we have not yet talked about finding eigenvalues. That'll actually be saved for a future section, but what we'll start out with is finding the eigenvalues of a triangular matrix. And the theorem says that they are on the main diagonal. Triangular meaning zeros either above or below the main diagonal. Okay, and so we're going to go through a proof. All right, and for our proof, we're just going to consider a 3x3 case because it's easier to write down, but it generalizes to an n by n matrix without too much difficulty. And we'll say if A is upper triangular, then A minus lambda I has the form as follows. A minus lambda times the identity is equal to A11 minus lambda with zeros below it, A12, A22 minus lambda with 1 0 below it, A13, A23, and A33 minus lambda. Right, that would be upper triangular. All right. Now, what do we know about eigenvalues? Lambda is an eigenvalue of A if and only if the equation A minus lambda I times x equals 0 has a non-trivial solution. Okay, that's how it was given in the definition. So that is, it has a free variable. Okay, and when does it have a free variable? That happens if and only if an entry, because we're already triangular, an entry on the main diagonal is 0. Is 0. All right, and then when does that happen? Well, it happens when that happens, or I'm going to say if and only if again, because I've said that a couple times. This happens if and only if lambda equals A11, lambda equals A22, or lambda equals A33, and that just comes that just comes from those diagonal entries setting them equal to 0. And there we have the conclusion to our proof, right? The eigenvalues are on the main diagonal, because that's what would need to be 0 to have A minus lambda I times x equals 0 have a non-trivial solution. In this next example, we don't have to do too much work. We're just going to kind of address one key connection here. And what we see is we have two matrices, A and B, and they are both triangular. A is upper triangular, and we can see that its eigenvalues are 3, 0, and 2. B is lower triangular. We can see its eigenvalues are 4, 1, and 4. Well, so just 4 and 1. But I want to focus on, for this example, just the eigenvalue of 0 in matrix A, and ask the question, what does it mean for a matrix to have an eigenvalue of 0? So the lambda would equal 0 in our AX equals lambda x, AX equals 0. But that equation is really just equivalent to AX equals 0. Right, and if 0 is an eigenvalue, then it means that this equation has a non-trivial solution. Okay, so think back to something in the course where we addressed the equation AX equals 0 having a non-trivial solution. Well, what does that mean about the matrix A? It means that A is not invertible. Cool. So this ties that this ties the current topic back into that unifying theorem of the course, that when we have an eigenvalue of 0, my matrix is not invertible. And we close out the section with a theorem. We're not going to do a proof of it. It's in the text. You can choose to read it if you want to. But this is the last piece of this section 5.1. If you have a set of eigenvectors v1 through vr that correspond to distinct, which means each one has its own eigenvalue, lambda 1 through lambda r for some matrix A, then the set v1 through vr is linearly independent. So if you have a set of vectors that each correspond to their own unique eigenvalue, they are linearly independent. And like I said, the proof is in the book. We're not going to go through it in this video. Thank you for watching. That's the end of the section. Do some homework, ask some questions. Let me know if you need help with this. Thanks for listening.